differential equation is y double prime minus xy equals 0. We're going to use the area equation as an example because it has an explicit dependence on the independent variable x. It appears right in there inside the equation. So you'll get to see why it's taken as an input into the function that SciPy's ODE int takes as an argument. So let's go ahead and make some substitutions. So we need to put everything in terms of a first order differential equation in terms of a variable z. Z can have be a vector, in other words, multiple variables. So let's start with z naught, and that's always our lowest order, well, 0th order derivative, so no derivative, it's just y. And then z1 will be our first derivative, dy dx, y prime. And we don't need a z2 because our highest derivative is y double prime, and we only need up to the second highest order derivative. Alright, so now we need to express the derivative of the z's in terms of the z's themselves. So let's take z naught prime, and that's just y prime, or z1, and then z1 prime is equal to y double prime, but y double prime is equal to xy. So we write x, that's fine, and we would write y here, but we can't. We have to write z naught. So we have to express it just in terms of the independent variable and our new variable z. So now we can take this and put it into SciPy because we have this. It's an equation that relates the time derivative, or the derivative of z's, in this case it's with respect to x, in terms of just the z's themselves. Okay, so from SciPy dot integrate import ODE int maybe, and import matplotlib.py plot as plt, import numpy as np. Let's see. Alright, let's create a function. Call it f. That's going to take in two arguments, z and x. Often we've done z and t, but we'll call it x in this case. And we need to express our dz, basically, in terms of our z1 and z2, or z0 and z1, excuse me. So our first, let's see, I'll just show dz naught time the derivative of z naught is equal to z1, that's z element 1, and dz1 is equal to zx times z element 0. And notice we've actually used this argument that comes in, the independent variable. And then we can just return dz naught, dz1. We can make an array, it doesn't really matter. So sometimes I've done, because z is an array, maybe it would be nice to return a numpy array instead. So let's do dz is equal to the numpy.array, or zeros maybe, z.shape, whatever size z is, the time derivative of z will be. And so dz element 0 is equal to z1. Here, we'll do this. There. Okay, so that's our function. Let's go ahead and make a call to ODE int to see what it looks like. So solution, which is just the z's and a bunch of, well, we need to create time points, or the x points in which to evaluate it. So x equals numpy.array from, let's say, 0 to 10. Let's do 100. I should probably want lin space. because I don't really know how long it goes, so up to 10 is a good guess. And let's say y is equal to ODE int of our function f with initial starting solution. Let's see if area function has any. Let's see what it looks like here. The area function, let's see, AI, it's starting at 0, which it looks like it takes negative values better. So let's look at it from negative 15 actually, according to this plot, and let's start it at 0.26 or whatever it shows there. Something like that. Maybe it's a little higher than that, 0.3. I'll give that a shot. So let's actually make this from negative 15 to, what was the limit on there? 5. And we'll give z naught. It can be a NumPy array. It can actually just be a regular old list. It'll convert it to a NumPy array for us if it needs to. 0. No, the time derivative. I think that b. Let's see. Standard choice. Oh, well, I don't know. What does the derivative look like? It looks like the derivative is 0 there. So, because the slope looks like it's around 0. So I'll put 0.3. Okay, and so that, and then we need our time points, or x. I think this is the correct order. If not, we'll figure it out later. Size the array, so let's try that. Let's try it's the other order. Oh, we need to return something. How about that? Return DZ. And maybe that was the wrong order. So let's plot x versus y. Let's go ahead and turn inline on. Matplotlib inline. Much better. But we've got something wrong. Okay, I think part of the problem is that our y is really two-dimensional. So see y. So we really want just the function y itself. So let's go ahead and plot y, the 0th column. So all entries of the 0th column. That's no good either. Where does it go up to here? It looks like it goes off. No, it should settle down. Let's only go up to 0 and see if we just mess something up. So make this go to 0. Okay, looks like maybe we've got something right. Oh, we plotted at 0.3 instead of 0.30. 0.3 and 0. Alright. Let's try that again. Let's also go up to 5 this time. Noose. Let's see, what do we have here? Looks like that settles down. That's what we want to happen. This is at 0, or at negative 15. The y value is, maybe it's closer to 0.25. Let's see if we bring it closer, if it works. 0.25. Maybe it's really sensitive. No. Okay, I've done a little research, and I guess I was expecting that we would get a solution that looked like this because I wasn't really paying much attention. So it turns out that the area function, when you solve it analytically, you get a linear combination of this AI and this BI. And one of them goes to infinity, the other one goes to 0. So if you get any part of this BI in there, then your solution is going to go off to either positive or negative infinity, depending on whether it was a negative or positive sign wherever you started, I guess. So it's not unreasonable that we are getting a crazy solution that blows up or down for large values of, or anything really greater than 0. But we do see something that's characteristic of the area function, or that is, what is it? How does it describe it? Rapid oscillations. Let's see. All right. When it's negative, they oscillate around 0 with ever-increasing frequency and ever-decreasing amplitude. So increasing frequency, oops. Well, that doesn't really make sense. I think it means when it gets more and more negative. So let's see if it, all right, so let's see if we go back further in time. Let's go back to negative 100. And let's do a lot more evaluation points. We'll see. Okay, so frequency does appear. Let's go a little bit less far back. So the amplitude as we go back is decreasing. The amplitude is decreasing and the frequency is increasing as we go further and further back. So that seems like this is a reasonable solution. Let's move on and do another example. I think that we've got this one correct. So I'm going to give the example of gravity acting between 2 point masses. So I don't know why that happens. All right, let's have a point mass here, and it'll be M1. We'll have another point mass here, and this will have M2. And we want to know what their gravitational attraction to one another is. Well, this one's going to experience a force acting in this direction. So, and this one is going to have an equal and opposite force. All right. Now this is the x component. Actually, this is, let's just draw it as a vector. So I'm going to give it an underscore. All right. And so actually, maybe this diagram should have been shown a little bit differently. Let's draw it actually. Here's my mass 1. And here, that's getting pulled by F, and this one's getting pulled also by the same F. Okay, just to show that it's not necessarily only horizontal. So let's give coordinate system X and Y. Okay, so this has two components, both a horizontal and a vertical component. So let's break it down. So this is a vector. And so basically, we've got another way to do this is show that it has both horizontal and vertical components. So there's an Fx, and then this getting pulled up by a force Fy. And this one up here is getting pulled down by an Fy and getting pulled over to the left by an Fx. Okay, let's find out what F and Fx and Fy and all that stuff is. Okay, all this is the same, just different representations to show what's going on. Okay, so we know that the gravitational force is, force due to gravity, equal and opposite, is mass 1, mass 2, times a gravitational constant g over r squared, where r is the square root of the squares of the distances between these two things. Okay, so let's say, I guess we need x2 minus x1. squared plus y2 minus y1 also squared. All right. And so since it's r squared on the bottom, it's really over this, and there's no square root. So that's the force. Let's find the acceleration. Well, it's also, we've got an fx and an fy. So I guess that depends on the angles. Okay, so we've got to do a little bit of geometry here. So let's do the geometry part separately. The distance between these two is x2 minus x1, where this is at x2 and this is at x1, and the vertical distance is y2 minus y1. We need to wait for this to catch up. Okay, y2 minus y1. Okay, is this vertical distance. Okay, and this is r. So if we take a look at this triangle here, we could say that we have an angle theta, and so we would typically say that, you know, fx is equal to f, whatever the magnitude is, that up here, times cosine of theta. But cosine of theta, if you remember from trig, is x2 minus x1 over r. And fy, likewise, is f times sine of theta, but that's just y2 minus y1 over r. Alright, so we've got the forces in the x and the y directions acting on our two masses. Now what does that give us? Well, some of the forces is mass times acceleration. Each mass has only one force acting on it, so we've got some of the forces on body 1 is just F. Well, Fx, well, let's see, in the x direction, just Fx, that's just m1 times x double dot, the acceleration in the x direction. Likewise, Fy is just m1 y double dot, y1 double dot, y. Okay, so that's just a fancy way of saying force equals acceleration, and the component force in the x direction is the acceleration in the x direction times the mass. Let's go ahead and make these masses equal, so we can just put, I guess, m squared here. Yeah, well, we'll leave them separate. Okay, so similarly, let's do the sum of the forces for so negative fx is equal to m2 x1 double dot, so forget what I just said, excuse me, x2 double dot, and negative fy is equal to m2 times y2 double dot. Alright, so we have a system of a lot of equations, 4 equations, and we have second derivatives for each of them. So our z vector is going to get quite big. That's okay. Let's go ahead and see if I can increase the size of this here. We'll just go over to the side here. Yeah, that'll do. Alright, so our z naught I'll take to be, and we can choose any order. We'll say that's going to be x. And z1 will be x dot. And we don't need an x double dot, so let's just do y. Z3 will be y dot. Z4 will be, all these are x1s and y1s. This one will be x2. Z5 will be x2 dot. Z6 will be Oh, we need y2 and z7 or zz. z7, handwriting is getting worse and worse. That will be y2 dot. All right. So we take the time derivatives. Z naught dot is going to be z1. And let's do all the easy ones first. Z2 dot is equal to z3, and so on. Z4 dot, or zy dot as it appears, is equal to z5, and z6 dot is equal to z7. Okay, let's do the harder ones. Z1 dot is equal to x1 double dot, which is just fx over x1 double dot. Z3 dot is equal to fy over, oops, this is wrong, fx over m1, right? Because if we take x1 double dot is equal to fx over m1. All right, and same thing for y. Y1 double dot is equal to fy over m1. So fy over m1. Got our z 5 dot. Yep, z5 dot is just negative fx over m1. And finally, our z7 dot is equal to negative fy over m2. All right, so kind of sloppy. Kind of new with this pad there. So let's see if we can integrate the motion of planet around a star, or two planets or something around each other, binary star system, without any other influences. Okay, so let's see if we can write that function. So we're going to define a function f of z, and it's going to take in time as the second, but it's not going to use time. T is, you don't see t explicitly in any of these equations. We just take the derivative with respect to time. So let's go ahead and make a numpy zeros size or shape of z. Call it dz. dz of 0 is just equal to z1. We'll take care of, but actually we're going to have a pattern here. That's c3, etc., right? So you see kind of where this is going. This is going to be the evens, and this is going to be the odds. So actually we can do this all in one step. We can take dz starting from 0 in increments of 2 is equal to z starting at 1 in increments of 2. That's nice. And then let's see. We're going to have dz element 1 is equal to fx. Ooh, okay, let's find out what fx is. So let's see. First of all, let's calculate f. F is equal to m1 times m2 times g all over r squared. Oh, what's r? R is equal to the square root of x2 minus x1. Well, let's find out what x2, x1, and all that stuff is. Is there a good way to calculate this? I'm not seeing it. So I'm just going to go ahead and make these substitutions here. x2 is z4 minus z1 or z naught. Take that. We're going to square it plus something of the same form. So I'm copying it. probably wasn't any more efficient that way. Let's take y, so z6 minus z2 squared. I don't think that belongs. That looks better. Okay, I think that should do it. That's r, and so that gives us f, and fx is equal to f times what? Fx x2 minus x1 over r. So times z4. Well, actually, here you're going to see this quantity so much, so let's just call something the difference in the x's is z4 minus z0, and the difference in the y's is z6 minus z2. So we can make this a little bit nicer. Dx squared, and we'll make this dy squared. And fx is equal to f times dx over r. And fy is equal to f times dy over r. Cool. So dz element 1 is equal to fx, dz element 3. Oh, this has to be over m, right? m1. dz element 3 is fy over m1. dz element 5 is f negative fx over m2, and finally dz element 7 is equal to negative fx or fy over m3. All right. So m2, excuse me. Silly. So where are we going to get all these m1s and m2s from? So you can accept them as arguments in here, but they're not going to be able to be passed in by the function ODE int. Well, they can, but just not by default, and I just don't like to remember how to do that. So I'm going to say this should have been a z. I really should have called that z instead of y, but no. Yeah, because it's all the z variables. Yeah. Okay. So let's go ahead and call it z is equal to ODE int. We're going to integrate our function f. We'll have a z naught. What should our z naught be? Let's go ahead and make all right, if this pen divine will come back to life. Okay. Let's say that m1 is right there on the x-axis. All right, and so it'll be at 0, 0. So x1 will start out at 0. y1 will also be 0. Let's have it fixed to begin with. x1 dot is initially going to be 0, and x2 dot is also initially going to be 0. Great, that's easy. And then let's make this guy, let's make that kind of like moving up, but not over. So we'll make it unit distance across. So x2 at time 0 is going to be 1. y2 at time 0 is going to be 0. x2 dot is also going to be 0. And y1 dot, or y2 dot, is equal to be 1. So I'm just imagining it being at this position kind of moving up, and I'm thinking that gravity is probably, if this is a lot more massive than m2, then it's going to be like this is the sun and this is the earth, and it's going to kind of move around in a circle or something. In general, some sort of ellipse. Yeah, it just depends on, it depends on how fast it's going, whether it's going to be a circle or an ellipse. So let's say M1 is going to be 100, and M2 is going to be 1, and we could actually plug in Earth and Sun masses and things, but let's not. All right, Z at time is 0, 0, 0, 0, 0, and 1, 0, nope, 1, yeah, 0, 0, 1. And we can make that an NumPy array, but we don't have to. So let's start Z0, and we'll go from time NumPy dot linspace from 0 to, I don't know, 10. We'll see where it's going and how fast it seems to be moving. 100, oops, 0 to 10 in increments, in 100 increments, and T. And so Z is going to give us all kinds of stuff. And these are all X1. Let's unpack it. Oh, no, it's not going to do what I want it to do. So let's just say that we want to get the position of X2. X2 is going to be Z element 4, or Z all rows of the 4th column. And let's also get its Y position. So Y2 is Z. It's because we expect this thing to be moving in some sort of circular-ish motion, or ellipse anyways, depending on how fast it's going. Okay. Yeah, so we got that out, and let's plot it. plt.plot. Let's plot X2 versus Y2, and so that'll show its trajectory in space. All right, got a little issue. F takes exactly 4 arguments, so I never did that. Okay, fine. Let's go ahead and look up how ODE int takes in parameters. Args. Okay, I can pass in args. Now, how does it take it? Extra arguments to pass the function, and I think that this ... means it's all, each of the arguments comes in separately. So where's examples? Okay, so I pass in args gets M1, M2 as a tuple. G is not defined. Same thing with G. We gonna have to take in G as well. And I'll just make it 1. Or G. Size the array returned by func does not match the size of why not? Because it's none. Return DZ. I made the same mistake again. Oh boy. So it looks like maybe it's going on for too long in time, given how fast this system seems to be moving. So let's go ahead and let's see if we make this a lot finer. Ooh, somewhat circular. Look at that. All right, so I think that we're getting all kinds of funny stuff because everything's just happening too fast. So let's go for 0.1 second, and we'll go for 1,000. Look at that. All right, so let's see this a little bit more closely. All right, so let's go for 0.3 seconds. Yeah, it looks like it is. Oh, I see what's going on here. It looks like it comes in and it passes really close. And when it passes really close, the force is going to get really high. So I'm going to make the sun a little bit less massive. Yeah, there we go. So that it doesn't, yeah, because, oh, actually before, that thing was so massive that look at the scale here, 0.06. So this is actually a really serious ellipse. Let's see if we can make this plot so that, matplotlib, so that the axes are square, I think, or equal, something like that. I forget what it's called. Matplotlib square. Axis equal. Not equal looks like ellipse. Equal looks like circle. Yeah, it should look, we want the axes equal. PLT.axis equal. Alright, so see, that's like really tight and it's passing right by that thing. So we want this to be a little bit less massive, and we'll go for a little bit longer in time. And we're still crossing right in there, so let's make it go a little bit faster, because I don't want it to pass by there. Or maybe what's going on is, I think that, well, let's see what the position of the sun is in this case, x1, and so I think the sun is getting pulled closer, so it's starting out here, but it's actually probably going in a little bit. Let's make it a little bit more massive, and let's give this still a little bit more speed. All right. More speed, more speed. Let's start them a little bit closer. So let's put the sun starting at 0.5 in the x direction. No, we still get that going on. I think that there might be something wrong here. I'm just not liking the way this looks. Let's make it really heavy. Okay, we don't want it to move at all. Let's just give this thing enough speed. There we go, that's a lot better. So we gave this thing plenty of speed. Oh wow, I think it almost worked out perfectly. So before, we were getting these ellipses, right? And this thing was moving real close there to the sun. It was moving, which is going to stay right around here. But then I gave it enough speed in the y direction, so, and it starts, you see that 0, 0 starts getting further inside. I just didn't like that look. 0, 0, so this is looking like a more proper ellipse now. And so then when we make it even bigger, gravity's a little unintuitive sometimes, but this looks really good, right? Yeah, that's going to be almost a nice ellipse, and the sun is going to stay kind of in the center there. I think that's what I was looking for. Okay, and let's just plot the sun's motion to y1 is equal to z2, and and x1 is equal to z0. So we'll plot that, and that should go maybe in like a little bit of a motion in the center there, just showing that it's just staying put, x1 and y1. Yep, it's not moving very much at all. I'm just staying kind of right there in the center. Okay, so that makes me a little bit more confident. A sanity check that a really massive thing in the center, and then a light satellite, which I'll pretend is the Earth, that's moving sufficiently fast that kind of goes in an orbit, and we can predict its orbit for a really long time. Let's let it go a few seconds long, etc. So here we go. Yeah, I think I'll leave it at that.